So can you see my screen when I'm...
Yes, I can see your screen.
All right. So we are going to talk about the Riemann integral. We are going to talk about Riemann integral. So I'm going to give you some few definitions that they're going to help you in order to answer any question based on the Riemann integrals. So if you are given a function, which is f, and this function is mapping from a going to real number, then this a is an interval. It's an interval. It's an interval, and this function is differentiable. It's differentiable. Then it means that this function f, there will be a function called f also, which also that it can also be differentiable also from a to r. So this function called f, we can find a different, we can differentiate it in such a way that it's going to be equals to this function that I just mentioned here. Then if this is true, this is called the f, this f here is called a primitive, or this f is called a primitive of f. This function f is called a primitive of f. So this definition, you can just know it, but you don't have to memorize it. So the definition that is more important now is this one, whereby if we have a and b, this is just an interval, which it can be a given as a number, be given as an infinity, it can be given as, or given as infinite interval. Then a partition P of a of interval a and b is a finite set of a points. It's a finite set of a point which we can write them as x0, can be x1, and then to xn. So this satisfies that, it will be satisfying that our a, which is this here, equals to x0, which is going to be less than x1, which is going to be less than the remaining values, which is going to be less than xn. And this xn here is going to be equals to ab. So the most important definition that I'm going to highlight before here is the definition that I'm going to state now, which we're going to be using in answering almost many questions. I just did this question with you without giving you more definition before. Then the sum the upper sum the upper sum of f relative to P. P is our partition, is defined by our U of P. U of P, which is equals to N sum of I equals to 1 of Mi. This is capital letter Mi, whereby it's going to be multiplied by Xi minus Xi minus 1. So in your books here at UNISA, they don't use I, they use K. So you will find that in your memos when you're writing, when you check, you will find that instead of Xi, they're going to be saying Xk. So, but it's still the same process. We use the same process whereby our M, this M here, Mi, is equals to supremium. We already talked about the supremium when a function is bounded above and sub-infimum when a function is bounded below of f of x into our xi minus 1 is less than or equals to x, which is also less than or equals to xi. So this is the definition of the Mi. So the lower sum of f relative to P is defined also as L of P equals to N sum of I, which is equals to 1 Mi in brackets Xi also minus Xi minus 1. So if we check something here, Mi minus 1, so whereby our Mi, if you check something, when I use a lower sum, I'm using a small letter m. So you must also use the small letter m, even if you are using small letter mk. Then m, whereby m is infimum of f of x into xi minus 1 is less than x, which is less than xi. So what we just did there, we just define the upper sum and the lower sum. So now we're gonna talk about, there is a definition. It's not more of like a definition or not really a definition. So there exists also a number m and also a number n m with m greater than or equals to f of x. This thing here does not mean anything. Let me delete it. Yes. For all x which are element of interval a and b. So when this is happening, our L, we can rewrite our L of P equals to M. If you check now, I'm writing the capital letter M in the lower sum into n minus n sum I equals to 1 of x I. There is this M is no longer having I. If you must take that into account, minus 1, which this it can also be equals to, we can just say is M in brackets B minus A, the interval values, which means if you have this number for supremium Mi, then you can just multiply to get the lower sum. And then our upper sum is going to be using small letter m into n sum of I equals to 1 of the same as xi again minus xi minus 1, which is going to be equals to m in brackets b minus a also. So those are simple. Instead of working out in a hard way, you can use this one if you are given this condition here, the condition that I just stated now. So you will see how we apply that as time goes on. So now we're gonna go to one of the definition, but this definition you have been using it in calculus. So the definition, it says a function. If you have a function, if you have a function defined and bounded, this function is defined and bounded. And bounded on an interval, which you can say A and B, is Riemann integrable on AB if and only if and only if L equals to our L equals to U. This L is the same as this one here, and the other U is this one and the other L there. So if this implies that if L equals to U, it implies that we can get an integration of AB f of x dx. So in other condition, there will be a condition whereby when you calculate, you will find that your L is not equals to U. There will be that condition. So as long as the L equals to U, then we can also be able to integrate that function. So now, in your question papers, you will find a simple question like this one. They can test you with this very simple question. So the first step, you have to know how to do this question that I'm going to be doing now. A question can say, prove that f of x, which is equals to x, is Riemann integrable on interval 0 into 1. So here now, in this question, if you check, we are given a function and you are also given an interval. So we have to prove that this function is Riemann integrable on 0 into 1. So when we prove that, we are going to tackle it step by step. The first thing that we have to do, we have to know the partition. We have to show the partition. Showing the partition, we just have to state it. So for each, now I'm answering that question. This is a solution. For each n, which is an element of natural number, we let P of n be a partition, be a partition be a partition of interval 0 into 1 given by, it's going to be given by Pn, which is equals to, it's going to start at 0. So what happened? We divide, because here in this interval of 0 into 1, we can subdivide this interval to be, maybe you can say we can divide it to be 0. Then after that, we can decide, okay, after 0, we want to add 0, 0,1. Can be 0, 0,1, 0, 0,2, up to it goes to 1. So our interval here, we're gonna, instead of that, because we don't know how we're gonna be, what number we're gonna be dividing with, we are going to divide all this number by n. So when we divide all this number by n, we're gonna, in this interval, if we divide it, we're gonna have 1 over n, and then 2 over n, and then it can also go to 3, then until n over n, which this n over n equals to 1, we can just write as 1. So this is our partition. So when we have this partition, thus, we have showed that thus Pn subdivides what? Subdivide 0 into 1 into n subinterval, into n subinterval subintervals. So I already showed you that the subinterval is 1 over n, which is 1 subinterval of 1 over n. Therefore, we now going to calculate our mi. We're going to start with the mi. So our mi, according to the formula that I gave it to you, our mi equals to sum of, is the sum of, is n sum of I, which is equals to 1 of f of x I minus 1 minus, is f of x I, oh sorry, not that. So for the mi is in the form of, we must remember that is in a form of the infimum. So the mi is going to be equals to f of x I minus 1, the lower one. And then when we have that, so in our function here, for if we substitute f of xi minus 1, we're going to find that in our function of f of x, we're going to find that this is going to give us I minus 1 over n. So when it gives us I minus 1 over n, I'm going to show you how it comes. And then also the mi, which is equals to is going to be f of xi. So in our f of xi is going to be I over n. So why am I I'm using I over n? Is because of our I, this f of xi minus 1, we divide, when we substitute in in xi minus 1 in x, our f of x, remember, equals to x. So when we substitute I minus 1 is going to be, we get the subinterval, we divide by n. When we substitute I to that equation, we're going to divide by n. So even if you don't use that method, we can still use, remember our mi is the infimum of f of x into xi is less than x, which is less than xi minus 1 is less than x, which is less than xi. So normally you just take this I minus 1 in the function, then you divide by n every time. So now when we have that, we know the mi, and we also know this big small mi and the big mi. So now we can get our u of p. To get our u of p, we know that is mi is n sum of I equals to 1 of the big letter mi in brackets f of xi. In brackets f of xi, it's going to be f of xi is going to be f of xi, like this way. Then this is going to be our mi is I over n. Okay, let me write some first. It's going to be n sum of I equals to 1. Our mi is going to be I over n dot our f, this is mi, then our f of xi, which is interval dividing this, is going to be xi. Our xi only is going to be 1. The subinterval that is subdividing this is going to be 1 over n. So normally, which means this one, when I put f of x here, it will make this equation to be wrong. So I'm just going to have to say this is pi is going to be mi into pi, or mi into dot pn, which is our pn is going to be 1 over n, which I can just write the subinterval, which is 1 over n. So now when we have this, you will see that we are going to have 1 over n squared, which we can write it as 1 over n squared outside, because this is just a number, into n sum of I equals to 1 of I. This is that I. So this equation here, if you work it out mathematically, you will find out that is sum, they are given n into I equals to 1 of I. If you work it out, is equals to n in brackets n plus 1 over 2. So how do you work it out? You can first substitute. You work it in the form of a sequence. If you say substitute 1 is going to be 1 plus 2 plus 3 plus 4 going upwards. So this is like, you will see that it's an arithmetic sequence whereby the difference is 1, 1, 1. And the total sum of this is your Sn, when you use arithmetic sequence, is n over 2 in brackets 2a. Your a is going to be 1, this letter plus n minus 1, and the difference is 1. So if we group everything there over 2, you will see that here we're going to have 2 plus, in brackets, n minus 1, whereby if you, we're going to have n over 2, in brackets, this one plus this one is going to be n plus 2 plus 1 is going to be n plus 1. Then when we multiply this, we can rewrite it as n plus 1 over 2. So I just prove it to you that this in is the same as that. So this one, it was not necessary for me to do this in this question, but I'm just showing you how it came. So now when we have this one here, we can write our equation as equals to then equals to 1 over n squared. Therefore, we're going to put this, which is going to be n, in brackets n plus 1 over 2, which is going to give us, if we multiply here, is going to give us this. We'll cancel with 1 there of n. We're going to be left with n plus 1 over 2n. Then this is equals to what? Lu of p. So we're going to end there for this one. Then when we end there now, we're going to calculate also L of Pn. L of Pn, we just calculate U of Pn. So I'm going to delete here. Then we calculate L of P. So even L of P, we use the same process. When we use the same process, it's going to be N sum of I equals to 1. But remember our N of P, it was I minus 1 over N. Multiply by, we're going to multiply by N for the one that we are subdividing with. Then here we're going to take 1 over N squared, which is equals to N sum of I equals to, here is squared, yeah, sum of equals to 1 of I minus 1. Then this one here, when we work it out, we can work it as 1 over N squared. We can put brackets N sum of I, which is equals to 1 of I minus N sum of I, which is equals to 1 of 1. We can just write 1 like that. So normally this sum like this way, the answer, it will be 1 over N squared. This one we already know that is N, I already prove it to you, plus 1 over 2 minus this one here. When you have N, if it's a constant, you multiply by N, it's going to just be N. Then if we do our calculations, you will see that our N squared is going to be equals to the everything there minus is going to be N in brackets N plus 1 minus 2N over 2. So we can divide by x squared both sides. Then we're going to have N plus 1 over 2. And if I divide by N squared here, I divide this one first, then minus 2 over 2N again. So this one, I was just trying to simplify it so that I may not do a wrong calculations. Then this 2N here, you will see that we're going to have N. This one, this is minus here. It's going to say 2N, N plus 1 minus 2 is going to be N minus 1. If you check that if you do your calculation properly. So now we have found that our L of P equals to N minus 1 over 2N. So now when it equals to N minus 1 over 2N, so this means that our N minus 1 over 2N is less than or equals to L, which is also less than or equals to U, which U is less than or equals to, we got it was N plus 1 N plus 1 over 2N. So now when we found that, if we work out now about the limit, the one we're using, if we get the limit when N approaches infinity of N minus 1 over 2N, you will see that this limit we can divide by N both are everywhere. When we're going to have limit when N approaches infinity of, if we divide by N here, we're going to have 1 minus 1 over N divided by 2. So if I now the limit, you know that this limit of 1 over n is 0, then we're going to have 1 over, it's going to be 1 minus 0, it's going to be 1 over 2. Then if we also do the limit, when n approaches infinity of n plus 1 over 2n, which is also we divide by 2, we're going to have limit when n approaches infinity of 1, we divide this n by 1 plus 1 over n, divide by 2, we divide 2n by n. Then this one is going to be, if we substitute here, is going to be 1 plus 0 is going to be 1 over 2. So now you will see that the limit when n approaches infinity of n my plus 1 over 2n equals to limit when n approaches infinity of n minus 1 over 2n. Therefore, this implies that our L of P, even if you just write L, not L of P, I was just showing you that you must take into account that I'm talking about L of P, but you can just, our L is equals to what? Our U. So this implies that this function f of x, you have proven, I've given you the definition that if ln equals to u, then it means that it's a Riemann integrable. So this implies that f of x is Riemann integrable. So just by doing that, you have just answered the question that we just did now. So f of x. So the same method that I was showing you how I was doing, it applies to all the questions in your question paper that you have. It may be only different because the question that you might get in your question paper, sometimes it can be f of x. Maybe they can even give you x cubic plus 2. So, but we use the same method. So this was just an example on how you prove that a function is Riemann integrable. So now we can proceed. Or do you have any question based on the question we just did now?
Can we do an exam paper example?
Yes, we're going to do it here. We have much time today. So I'm just giving the only thing that now I'm giving it to you. I just want to give you the definition so that you can remember if you or when you watch this video, so that you can know them to apply to any questions that you're going to approach based on this one. So that one was just an example, but I think it's in one of your question paper, even though I'm not sure which one. So let me give you one more. We are left with few ones. Then we're going to do questions. We're going to do a lot of questions. So we also have this Riemann condition. So Riemann condition, it says let f, if we have f, be defined and bounded on interval a and b, then f is Riemann integrable. On interval a and b, if and only if every e greater than 0, e greater than 0, there exists a partition P of AB such that U, this one is very important definition, U of P minus L of P is less than epsilon. Sometimes even if you put absolute is fine. So this question, every time, in almost every question in your UNISA, they normally ask you this definition, this condition. I have checked that. So you must just remember, let F be defined and bounded on AB, then F is remain integrable on AB. If and only if every E greater than 0 there exists a partition P of AB such that LU of P minus L of P is less than epsilon. So this one, they always ask it. So you will see every question that we're gonna be doing that we're gonna be answering this question. So you must rewrite it down somewhere. It's only, they normally come with 3 marks. Just to state this, what I just write it now. So the question that I just gave it to you is very, yeah, it's fine. So now we're just going to go to, not now, okay, to do some few, it's only one definition we are left with, but I'm just gonna state a theorem. You don't have to remember theorem. This theorem is more important, but you don't really have to remember it. If F is monotony, the monotony on interval A and B, then F is Riemann integrable on AB, on interval AB. So this is just a theorem. You don't really have to prove it unless otherwise, if they ask you to prove it, then we're gonna find it in the question paper. So I'm just gonna also state few things. Then we're gonna be done with the theory. We'll go to question papers. So we also have properties of Riemann integrals. The properties of Riemann integrals, they are more the same as the one you have been doing for calculus. If you have an integral of AB, whereby this integral it have alpha f of x plus beta g of x dx, then you can rewrite this as alpha integral of AB f of x dx plus beta integral of AB f of x g of x dx. So now I'm not gonna write all of them, but let me just, yeah, this one is more important. If you have integral of a b again, which is f of x dx, you can write it as integral of a going to c f of x dx plus integral of c going to b f of x dx, whereby this c that we just introduced now is in between a is less equals to c, which is less is c. A is less equals to c. which is less equals to b. So if the other one, if f of x is less equals to g of x, then this also implies that the integrals, I would just say integral of f is less than integral of less equals to integral of g, ab, ab. And one more, the integral of, these are just property, absolute value integral of ab of f of x dx is less than integral of ab. You must remember that. It will also help in some other subject. Absolute dx. So the properties, we are done with them. Then there is also one more thing that you have done it before about the mean value theorem, the integral of mean value theorem. Mean value theorem. So the integral of mean value theorem, it said that if we let f and g, f and g be continuous, on interval ab with a g of x, our function g of x greater than or equals to 0 for x, which is an element of AB, then there exists a C between, there exists a C between A and B. With the integral of AB, f of x, g of x, dx, which is going to be equals to f of c, integral of AB, g of x, dx. So this is just a formula that you must take into account. So you will just do this one as your homework, maybe if you are practicing, to show that you use is very simple. E to the power 2x dx equals, to show that this is equals to 1 over 4 e to the power 2 3 e to the power 2 minus 1. So you use integral by parts. Just try it so that you get integral by parts. You must use integral by parts. So let's go to the question. The first question that we're going to do we're gonna do, okay, yeah. The last, this, what we have been doing here today is the question which you'll find is almost a last question. So we're going to do this one here. Just give me 1 minute. So in this question, it says, state a criteria of a function f to be a Riemann integrable on the interval AB. Explain any notation you may use. So the criteria that they are talking about the definition that I just gave it to you, the criteria. That's why they say a criteria for a function f to be Riemann integral. The condition for the condition of that to be Riemann integrable is the definition that I gave it to you. Do you still remember it? The definition?
No, I forgot the definition.
All right. So now when you write this question, you write it simpler. I'm gonna go back to, oh yeah, let me go back here. Is we are answering 6.1. Remember your answers, they won't be really same as in there will be, they will talk about the same message, but then won't be really the same as the way the memo might state it. You're gonna let your f be defined. This is a criteria in order for, criteria means the condition. In order for it to be defined, you let the f to be defined and bounded. And bounded on interval AB, then f is Riemann integrable on AB if and only if for every a greater than 0, there exists a partition P. You can even say Pn is fine, of AB such that U of P minus L of P is less than epsilon. That's all. This is for 3 marks. I think is how many marks? Oh, it's 4. Yeah, it's 4 marks. Just to state that proof. So now the assay, you have that question. Now the question says,
I sent you the memo.
all right. Did you send a question paper? Let me check it. So if you check here in your memo, (6.1), there exists a partition P such that you will have that So these two here, u of p minus u of p equals to that. They are just giving you the definition of those u of p and u of l. So normally exactly the way, if you write it exactly the way I also wrote it here in words, they are going to, is the same thing. They are going to give you full marks. If you just write it exactly this is what, this is the condition that they want. So the u of l, the u of p equals to some supremium, you know that is just like defining those two. But the most important thing that they need this. So everything that we wrote there is the same. But you can, if like, if, because now you have seen how the memo is, you can rewrite it as it is. Then let's go to question number 2. Question number 2, it says consider f of x. This one is the one we can be doing the same steps, but we must arrive to the same answer. Says consider f of x equals to minus 2x plus 3, where x is greater than 0 or equals to 0 and x is less than 1. Let Pn be the partition 0, 1 over n, 2 over n. They already give us the partition of 0 to 1. Calculate L Pn and UPn. Hint, they give us that nk is that one. This is just a formula that I already proved it to you. So now we have to calculate L of P and U. So when we do that, it's very simple. We use all the basics, all the rules that we have been doing. So the first thing that we know, we were given a P. We can let P, because we are answering, P equals to, but it's given already 0, 1 over n, and 2 over n, and it's gonna be 1. Therefore, and the other thing, the function that we have there, if you take into account our f of x equals to, is minus 2x plus 3. So minus 2x plus 3. You will see, because of this 3 is a decreasing straight line, the decreasing, we can just say decreasing function. The decreasing function. So now we also have the change here, the change of our xk. If we say 1, if we say xi minus 1, let me use k now, k minus 1 minus xk, you will see that this change here is 1 over 2, every 1 over n. 1 over n minus 0 is going to be 1 over n. 2 over n minus 1 over n is going to give us 1 over n. So now when we have this 1 over n for the change, then the supremum of f, the supremum of f, whereby the supremum of f when we have a change, I will just write, or in the interval xk minus 1 into xk, is going to be equals to f of x k minus 1, the way I was doing in that question, which is equals to f of. So now when we put f of our xk minus 1, remember, is going to be, we are going to substitute in this equation, we are going to substitute k minus 1 in the equation. So when we substitute k minus 1 in this equation of xi, in of k over n, we substitute this k minus 1 the way I did with I there. So it's going to be my I k minus 1 over n this way. So now when we have that, we can say this is going to be equals to, we substitute f of x. Our f of x is this equation here. I already wrote it, the minus 2. Going to be minus 2. Where there is minus 2, we substitute with k minus 1 over 2n. Then it's going to be plus 3. So the total answer that we're going to get there we will get an answer whereby you can, but you can just leave it as it is for now because of we need to get the limits. So we're also gonna calculate the infimum of f. Infimum of f again is xk minus 1 into xk. So the infimum, this one, remember, here when I'm writing like this is the mi. This is the small letter mi, when you remember. But here we don't say mi, we say mk. Mk. So the mk now is the sum supremum of that is going to be f of xk, which is equals to f of k f of k minus over n, which this is going to equals to minus 2 in brackets k over n plus 3. So we can leave it like that. Now to calculate our L, u of Pn, our u of Pn, we know that is going to be n sum of the way we have been doing it of k, or I'm used to I, ne? Of k equals to 1 of 1 over n is the one for subdivision. And then we write our function, which is minus 2 in brackets k minus 1 over n plus 3. So if we make a calculation here, you will see that here we're going to have minus 2n squared, minus 2n squared, and sum of k of, we have taken this here outside, of k minus 1 plus 3 and sum of k equals to 1. So here when we have this 3 here, remember we have n minus 3 here, n over 3. This n here is gonna over n here. So now after this one, we will end up having, we can subdivide here, this k minus 1. We will end up having minus 2 over n squared and sum of k equals to 1 of k. This negative here multiplied by this negative is going to give us plus. We can say 2 over n squared and sum of what k equals to 1. But it's just 1. Even though I don't write it, it's not a problem. And it's still continuing with plus, continuing plus 3. This one I'm just rewriting. And sum of k equals to 1 of 1 again. Then this is going to be equals to, if we, after writing everything there, we substitute where there is nk, there we're going to have minus minus 2 over n squared. In brackets, we know that this is going to be k, in brackets k plus 1, according to this x, sum of k over 2 plus 2 again. This is just 1, the 2 over k n of k. So yeah, because here we are substituting, remember our n there is n, we are substituting as our k is 1. We don't write, we have to, it's supposed to be n, not k. I'm not supposed to use this letter k here. Supposed to be n. Even here it's supposed to be n. supposed to be n here. So now when we have this n here is n squared plus 3 over n. Also, we're going to substitute n. So the equation here is going to end up with this will cancel with this one here, and this 2 will cancel there. Then we're going to end up having minus n minus 1. Then this will cancel with this one. Then plus 2 over n. And this one will cancel with this. We're going to left plus 3, which if we rewrite it, we're going to have 2 over n minus n plus 2. So if we change this, I think we can even leave it in this format is fine, so that we don't make mistakes. You can leave it in that format. So if we leave it in that format there, but if we check properly, our answer is gonna be this one times this, going to be 2 over n squared. Okay, let me see what will happen. Okay, I'm gonna try to solve this one here so that we can get the right answer there. But it seems like as if it's gonna be a quadratic formula, because it's gonna be negative n squared plus 2n plus 2 over n, whereby it will cancel each other somewhere somehow. But it's fine, we're gonna work it out later. And the other thing that I did here, remember when it cancel here is n over n squared here, it's gonna be 2. Here it's supposed to say 1 is gonna be minus. Here there was a mistake that I did there. I just notice it now. So here is going to be n over that minus that. We're going to be left with minus 1 over, is going to be minus n plus 1 over n. And then plus this one will cancel. We're going to have 2 over n plus 3. Yeah, this one 3 is fine. So now if we work it out here, we're going to have n. If we write n plus this one and plus this is going to give us n plus 3 plus what? Plus 3 again, which this, if we work it out, is going to say n. It's going to be 3n is 4n plus 3 over n. So which we can say 4n over 3n plus, okay. And here it was, yeah, there is some mistake again. I made simple mistake just here in this part. Then if when we check properly, we have negative here. The negative sign is going to be negative n. It's going to be negative. This is like negative. Not okay. It's going to be n2 minus n minus 1 plus 3. Yes. So this one, 2 minus n plus 1 is going to be 1 minus n. We can just write it as 1 minus n. 1 minus n. So now when we multiply by 3, it's going to be 3n. Then this is going to be equals to 1 minus 2n over minus 3 minus n plus, yeah, it's going to be plus 2n over n. Whereby now when we rewrite this, you can see that the answer here we can write is going to be 2 plus 1 over n. Yeah, it's fine. 2 plus 1 over n. So we have proved that our p of n, p of n, u of n u of p equals to 2 plus 1 over n. So now we can work out L of Pn. L of Pn, we work it in the similar fashion. It's going to be equals to n sum of k equals to 1, whereby we're going to have 1 over n as a multiple of, in brackets, minus 2 brackets k over n plus 3 plus 3. So this is going to be n sum of k equals to 1 of minus 2 over n squared k plus 3 over n into n sum of k equals to 1 of 1, like that is fine. So now when we have this, we can take minus 2 over n squared out. Then we're going to be left with k, which we can rewrite is as n, in brackets, n plus 1 over n over 2 plus 3 over n. This is just 1 there. Then we can just say this is n. So now this will cancel with this one here. Then we're gonna left, and this one will cancel with this one. You're gonna be left with minus, that's n plus 1 over n plus 3. So this one, if we work it out, is gonna be minus n minus 1. Minus n minus 1 is gonna give us 2n minus 1 over n, which is going to give us 2 minus 1 over n. So we just found our L of Pn. So the question, if we reflect back to the question, the question says consider this function, let P, okay, calculate U of n, and okay. So the question, it only asked, according to the question, if we read it carefully, let Pn, it only asked us to calculate L of Pn and U of Pn, but it didn't ask us if this is a Riemann integrable. But just for in case, we can also take it further. When we take it further, we can just show that if we use the limit of n when it infinite of L of Pn, here is going to be 0, it's going to be equals to 2, which is equals to limit when n approaches infinity of the L, our U of L, we got that is 1 plus 2, which is still is going to be 2. So this function, which is still going to be U of Pn, which is still is going to be equals to 2. So which means this function is integrable, but the question only asks us to calculate that, not to show that this function is integrable. So it's going to be the end of this question for 2018. Then we can randomly select another one. This one I think is the same as this one and this one. Let's take this one here. I know that these questions are going to be in the last questions. So the last question here, question 7, state a criteria of a function f to be Riemann. So this one, I'm no longer going to state it because we just did it now. I hope you get what I'm saying. You understand what I'm saying?
Yes.
Yes. The same answer that you have in that memo is the same as for this one. And then consider f of x equals to minus x plus 1. Let Pn be, calculate UL, and we use the same process. Should we do it? because it's still going to be the same as this question. So there is nothing different between this question which we're doing, and you also have this memo for this question. You just do the same thing there. You copy where there is those values, where there is minus 2x, where you are substituting, you only substitute with this value. Where is it? You only substitute minus x plus 1. It's also a decreasing function. Then after that, you can see that is the same. Just that your value, when you are working them out, it won't be the same as this one that you did here. But where there is minus 2 here, you put outside minus 2, and then you k minus 1 over n plus what? Plus, here is plus 1. In this one here is plus 1. Like that, and so on and so on. So you can see that this question is similar to that one. You can't, I hope since we have done that one, you cannot get wrong with this one. So is f of x is in 7.2 Riemann integrable on 1? Explain. So when you explain, it's about the limit. If the limit, when you check the limit, if they are equal, if limit, when you check the limit of them, when they are equal, it means that is the same. So I think you can see that this question is the same. So explain why the following integral is an improper integral and determine by use of limits whether the integral converges or diverges. So this integral here, if we check it, is 3 over 4, 1 over x minus 3 dx, if we rewrite it properly. So this integral, when we do it, you will see that it's an improper integral. Why is it improper integral? It's an improper integral because you cannot just get this integral by using the properties of those properties that I gave you for Riemann properties. So in this integral, we have to do what? We have to use either the trig, we have to use a trigonometry, or we have to use substitution in order for us to get this answer. We have to let something to be equals to something in order for us to get this question, this answer. So in this one, which means the first thing that you have to do, you have to let your u equals to x minus 3. Then your du is going to be equals to dx. Then after that, when your du equals to dx, then you come to this integral of 3 into 4, whereby it's 1 over u du. Now when you have integral of 1 over u du, we know that this is going to be a logarithm integral. So which means you're gonna say, we know that integration of ln equals to 1 over x. So, but this one here, you can say is integral of 3 into 4 u to the power negative 1 of du, which is going to be integral of, which is going to be u to the power negative 2 over negative 2 given 3 into 4. Then after that, you can substitute the values. It's going to be 4 to the power negative 2 over negative, sorry, over negative 2 minus 3 to the power negative 2 over negative 2, there, which is equals to, this one here is going to give us 1 over 4. We can use your calculator. I think for this part here, you can use your calculator, because when I explain, I'm not using a calculator. It's going to take me time. It's going to be 1 over 16 divided by, or multiply by negative 1 over 2, which is going to be negative 1 over 32 minus, this is 1 over 9, which is going to be neg plus 1 over 9 times 2 is 18. Then you can use your calculator to get this value here. So, but let's check exactly what the question, what does the question says. The question is, explain why the following integral is an improper integral. So it's an improper integral because of we cannot use the properties of integrals, not integrals, the properties of Riemann integral. So do you have any question with it? Then it says,
No.
and determine by using limits. Okay. Then it says determine by determine. It says determine by using what limits. Determine by using limits whether the integral converges or diverges. So in order for us to use the limits, we can go to use the function. We can apply, if we don't have to work it this way, because I just worked it with calculus here, we can apply the mean value theorem. So mean value theorem is no, it's not gonna work, because when we apply mean value theorem, it's going to let us use the integral. So this part here in this question, we are not using, they don't want us to use this method that I just showed now. So in order for us to use the limit, which means we are going to get limit, we have limit, we are going to get limit when x approaches, you will say 3 into 4. You write it in this way, of 1 over x minus 3. But this one I'm still going to teach you. We are still going to do this for improper. Why am I using this x of the, normally when you rewrite it, you don't write it in this way. You write it in this format. The format that I used now is not the right one. Normally when we write it, we say limit when x is the mini, you can say mini sometimes, of, you write 3 into 4 of 1 over x minus 3. Then this one now, when it's like that, is going to be x over 3 is going to be limit of this 1 over x over 3. If we put 3 there, we'll see that this is not going to work. But if we put 4, it's going to be 1 over 4 minus what? Minus 3 minus again 1 over, we can just differentiate this. So when we differentiate this, 1 over x minus 3 to the power negative 1, when we differentiate it, it's going to be negative 1 x minus 3 to the power negative 2, which is going to give us minus integral 1. Yeah. So this is going to still be, if you check it, it's going to still be 1 over squared of this. But when we substitute 3 there, it's not going to give us anything. But if we differentiate using L hospitality, you will see that when we differentiate, everything is going to be 0. So when we calculate for the limit, the answer here is going to be over 0, which is equals to 1 over 1, which is equals to 1. So this function, it converges. We just got the limit, it converges. So we're still going to do more of this question. So do you have any question based on what we did today?
Yes, can you do 7.2?
7.2, okay, no problem. Let me just do it this side. So in 7.2, we have this function. So I'm going to just give me 1 minute. I just want to copy it. Seven 7.2, our interval is 0. Okay, it's fine. Is minus x plus 1. So our function there is minus x plus 1. Then when I do my 7.2, I will say we let our Pn, which is equals to 0 into 1 over n, is given this one, 2 over n into 1. Then our function f of x is equals to minus x plus 1, which is a decreasing function or decreasing straight line. Then the change of our xk is equals to 1 over n. Therefore, the supremum of this function, which is this one is mk, is xk minus 1 into xk, which is equals to f of xk minus 1, which is equals to f of, for xk minus 1, we're going to have k minus 1 over n. Then k minus 1 over n. Then we can just rewrite it as this is equals to, we substitute in this value, going to be minus k minus 1 over n plus 1 in our function of f of x. Mk, small letter for infimum of the same xk minus 1 into xk is going to be equals to f of xk, which is equals to f of k over n, which is equals to minus k over n plus 1. Then now we're going to get our u. We can start with u. You can start with any, even L. U of Pn. Our u of Pn is going to be n sum of k equals to 1 over n of, in brackets, we put as minus in brackets k minus 1 over n. Let me check. We are checking it here. Yeah, it's k over plus 1 plus 1. So this is the same as 1 over n squared n sum of k, which is equals to 1, or we can take it as minus here, of k minus 1 and plus 1 over n sum of n into k equals to 1 of 1 for this one here, this one there. Then this is going to be minus 1 over n squared of this one here. When we multiply, is going to be in brackets n, in brackets n plus 1 over 2 minus again, which is going to be plus because of this negative, 1 over n squared in brackets n plus 1 over n in brackets n, which is equals to this, will cancel with this one here. Then we're going to remain with minus n plus 1 over 2n, which is also minus 1 over n and plus 1. So you can use, even if I stop here, there is no need for me to keep going further. I can leave the answer as like this, because this question here, I have to prove that this is Riemann integrable. Then I'm gonna even, okay, before you even do anything here, what you can also do, you can say limit, you must calculate limit same time. You can say limit when n approaches infinity of u of p n equals to, for this one here, you will see that if we divide everything by n, we are going to have negative. This is the same as negative n, or let's just expand it for a little bit. This is going to be 2n minus n minus n minus 1 minus 2n minus 2n is going to give us minus 3 n minus 1 over 2n. Plus, we also have this plus 1 there. Nice. So, limit when this approaches this, you will see that if we divide here by 2, by n, we are going to be left with minus 3 plus minus 0 over 2 plus what? Plus 1, which is going to give us minus 3 over 2 is going to give us minus 1 over 2. This is the limit that we got. Then now we can go to L of Pn. Our L of Pn is going to be equals to also n sum of k equals to 1 over n in brackets minus is k over n. It was plus 1, yes. So this is going to be equals to 1 over negative n squared of, again, n brackets n plus 1 over n plus 1 over n yeah, it's gonna be 1 over n. Yes, 1 over n multiplied by n, 1 over n into n. Then this is going to cancel. This is 2 here. Going to cancel with this. We're going to be left with minus in brackets n plus 1 over 2n plus 1. So if we take also this is going to be equals to minus 2n, going to be minus n not minus n, is going to be plus n minus 1 over 2n. So if we get the limit, of this limit when n approaches infinity of L of Pn, we are going to get this limit here. We divide everything there by 2n. It's going to be 1. We're going to have 1 minus 0 over 2, which is exactly equals to 1 over 2. Therefore, we can just say L equals to what? U. Then it means that this function f of x is Riemann integrable. Did you see how I did it?
Yes.
Yeah. So this is the same process. Everything that I showed you, the limits. That's why I tell you that I want to give you the fact. The first thing that I want to give it to you is the definitions. The moment when you understand these parts that we are doing, every question based on this, you won't get wrong. So this is what I was having for you for today. Unless otherwise, if you still have any question. So now we just did this question, I did 7.2. And then I also show you with the limit. Is f of x in 7.2 remain integrable in 1? Yes. The answer is yes. Why is it true? You say yes. After that, when you say yes, limit when n approaches infinity of u of p equals to limit when n approaches infinity of L of p, which is equals to 1 over 2. That's what is needed. So maybe I want to ask you something based on, you said like the due date for assignment MAT 3705. There is no due date.
No.
Oh, okay. So they have been, but is it released?
Uh, what do you mean?
Like, do you have like a PDF questions of assignment 1 for that
We did it.
module?
We finished it.
Oh, okay. Are you not? I mean, is it we did MAT? You have MAT 3706, ne? Don't you do MAT also 3705? Complex analysis.
I'm not sure. One of those modules I don't do.
Oh, okay, no problem then. All right, then. If you have any question, you can ask me. I still have much time. Then I will gonna continue tomorrow at 5 p.m.